All right. So before we get started with today's content, I just want to give you an opportunity to ask any questions or have any, if you have any questions from Chapter 2 or the previous week's homework or anything. Yes.
Chapter 1, random sampling.
Okay.
I'm still a little confused on the differences between stratified random sampling and cluster sampling.
Okay. So stratified sampling, generally there is, kind of maybe different categories of people, and we call those strata. So, maybe you can have like different ethnicities or different genders or whatever it might be, different groupings. And with the stratified sample, you want to make sure that each of those groups are represented appropriately in your sample. Okay? With cluster sampling, you have subgroups, and what we're doing is we're not going to try to have each subgroup represented. We're just picking some of those groups, and we're hoping that the selection of our groups is then representative of the of whatever it might be. So, yes. Okay.
The homework. So I wasn't understanding why date of birth was a discrete variable. I'm still kind of confused.
Okay, date of birth and discrete variable. Okay, well, let me just go back to, I want to make sure I answered the question regarding cluster sampling and stratified sampling first. Is that okay?
Yes. But is it correct to say that in stratified sampling, you include all subgroups in your sample?
Yeah, so in stratified sampling, you typically don't have, more than 10 subgroups or something. It's a, quote, manageable amount, and you make sure that each of those subgroups are represented in your sample. So, if you want to do gender, you make sure that you have the appropriate number of males and females. Or if you have, racial categories, you make sure that each race is represented in your sample. Okay. Cluster sampling, you're just saying, I'm going to pick this cluster, and this cluster, even though there might be like 50 clusters or something like that. Okay, so your question about date being date of birth.
It was from the homework.
Okay.
Why was it discrete? Why is discrete?
Yeah, so date of birth is it's a weird thing. Date variables are strange, and so date of birth would be discrete because we could treat it as, I guess, kind of a numeric thing, being like the number of days since 0, 0, 0, or and because the date of birth, you're either born on Sunday, January 5th, 19 whatever, or Monday, January 6th, or something, and you can't. And these are distinct moments in time. If we were curious, up to the second of the day type of thing, then I suppose it could be continuous. But it's discrete just because you have, on the calendar there are 365 discrete days on the calendar. This year, 366. So. Yeah, you don't really have a continuum of dates.
What's another example of discrete? Like a comparison?
Okay. So, all right. So, if we had an accurate ruler, okay, we could measure your foot, the length, to extreme amounts of precision, right? Somebody might have their foot this many centimeters with this many decimal places. But when you go to the store, you have to choose a shoe size, and so you have a discrete selection of shoe sizes. You either buy a size 6 shoe or a size 6.5 or a 7 or something like that. They don't sell a size 6.2235 shoe, okay? Although your foot might actually be, some decimal place in terms of centimeters and whatnot, and if your toenails grow, then it probably changes a tiny bit every day and stuff like that. Although that's probably not ill-advised to pick your shoe size based on your long toenails or something. I don't know. But so continuous means you can have a whole bunch of decimal places, and that's fine. And discrete means you don't. Okay, means you have certain designated things that are possible. So if anything where the answer must be a whole number, that's going to be a discrete variable. Okay. But shoe size is one where it's not whole numbers, but it's still discrete because it has to be to the nearest half size. Okay. Any other questions? Okay, then we'll get started in chapter 3. And chapter 3 covers probability, okay? And so, let me just get the slide saved. And I hope everything with the website is working out. You're able to view the slides or lecture videos if you need to. I think that's the case. So I hope, when it comes to study, you have everything you need to study. Okay, so chapter 3, we are covering probability, and if I go, find the slide from. Where is it? From last week's class, I drew this and I said, last week we covered descriptive statistics, how to use numeric summaries to summarize our data, with things like the mean and the median and the standard deviation and IQR, okay? And then today we're going to start our talk on probability, and we'll cover one probability distribution. Next week we'll cover more. And these will eventually merge together when we get to statistical inference. So if it seems like what we're covering has very little to do with last week, that's not too far from the truth, except it will very much come together in a few weeks here. Okay, so in our class, we are taking a very classical view of probability, okay? And so I think we're kind of familiar with the notion of probability, and we have, other words to describe probability. But, I could make a statement like, I will flip a coin. The probability that the coin will land heads is 0.5, okay? And so, when I talk about probabilities, the probability is going to be a number between 0 and 1. A lot of times people kind of, just in conversation, they'll say like 50-50 chance or something like that. But, if we're going to be specific about the way we express probability, probabilities are numbers between 0 and 1 inclusive. Okay, and I think we're very familiar with the idea that if I were to flip a coin, the probability that it lands heads is 0.5. And if I were to kind of press you, what does it mean for us to say that the probability that the coin will land heads is 0.5? We might throw in other words like the chance that the coin will land heads is 0.5, or we might say the likelihood. Okay, we've got several kind of synonyms for the word probability, but what do these statements mean, right? For someone to say the chance that a coin will land heads is 0.5, What exactly does that mean? Okay, and so, well, in our class we take this classical frequentist view of probability, which is, probability can be thought of as the long run relative frequency, okay? Okay, meaning that if I were to flip the coin millions of times, billions of times, and if I were to keep track of how often it landed heads versus tails, and I kept, a running journal of all of this, then after many, many, many coin flips, the relative frequency that I would observe should be 0.5 or something very close to it. Okay, so then the idea is, if I millions or billions, okay, the relative frequency of heads should be very close to 0.5, okay? And this kind of, this touches upon the idea of maybe the empirical probability versus the theoretic probability, okay? So the empirical probability is really just kind of our observed relative frequency, okay? And for something like a coin flip, it seems silly to talk about the empirical probability, but it's often useful in situations where the math is hard. So we have empirical probability, which can be thought of as our observed relative frequency. And so, this would be like, so I flip a coin 100 times, it lands heads 47 times out of 100. Okay? So my empirical probability is 47 divided by 100, or 0.47, okay? And if we had never seen a coin before in our life, and we had no understanding of how, the physics of coins, and someone wanted to know how often does a coin land heads, our best answer at this time is that it lands heads with a probability close to 0.47, okay? Or, what is the probability that a coin lands heads? If somebody asks us that question, okay, we can respond something close to 0.47, okay? Now, with flipping a coin, it's very simple. There's just two sides, so it's either going to land heads or tails, and each side is equally likely, so it's easy to see that the probability that a coin lands heads is 0.5. Okay? But we often have very complicated scenarios, okay? Complicated things where the math or the physics behind them are not easy to understand, okay? But perhaps we have a good way to simulate this thing, okay? Or a good computer device or something, or even just running surveys and things like that, and you could say, so we could simulate different things, and so. The Super Bowl is coming up, and it's the NFL playoffs, and a lot of websites will say we estimate this team has this probability of winning and things like that. Those things are based on simulations. Okay, there's no mathematical formula that says this is you plug in these numbers and it gives you the probability that a team's going to win. But they've developed complicated computer programs that try to simulate how a football game might be played out. And they run this game, they run this simulation thousands of times, and based on basically the empirical probability that they observe after thousands of simulations, they get an idea and say, this is the probability that this team will win the game. Okay? So it's very useful in situations that are quite complicated, okay? And of course, the quality of these predictions are going to be heavily dependent on the quality of the simulation, right? So if somebody did a poor job programming the simulation, you're not going to have good predictions, but at certain points in time, this might be the only way to really kind of get the sense of a probability, especially when there's no direct way to approach it, okay? So this is useful when trying to calculate probabilities of complicated outcomes. So for example, and on the other hand, we have theoretic probabilities. Okay, and so theoretic probabilities, these are probabilities that are determined with mathematical rules. Okay, and so in simple situations, the rules are easy to apply. Okay, so in relatively simple situations, we can apply these math rules. And so for example, we say something like coin has two sides, each are equally likely, so the probability a coin lands heads is equal to 1 out of 2, or 0.5. This is our theoretic probability that a coin should land heads. Okay, and we have what we call the law of large numbers, which basically states that the more times we simulate something, or the more times we actually flip the coin or carry out these trials, our empirical probability will get closer, or should get closer and closer to the theoretic probability, okay? Or we can expect the empirical probability to approach the theoretic probability. So as we perform more trials, the empirical probability should approach, or can be expected to approach, the theoretic probability. Okay, and this is how casinos stay in business. This is how the insurance companies stay in business, because they create their games. Casinos create their games based on theoretic probabilities. Insurance companies base their premiums based on their theoretic probabilities, and so as more and more people play the casino games, sure, you might have a few people who get lucky and quote win big, causing the casino to lose money. But in the long run, as more and more people play, the games are always designed to favor the casino, and so they can count on the empirical probabilities or empirical results matching up what they expect theoretically. Question?
So are theoretical probabilities derived from empirical?
No, the theoretic probabilities are calculated using these mathematical rules. The empirical probabilities are kind of what we observe. So basically we're just saying, if we do things a whole bunch of times, what we observe should match what we expect in theory. Okay. But sometimes the theoretic probabilities are too complicated to calculate out, such as with sporting events. Okay, we don't. It would be very difficult. I wouldn't even know how you could have a formula for how a sporting event should go. But we can kind of simulate these things, and we can run simulations over and over again and get empirical probabilities. So to have a formula for an entire game is very complicated, but you might be able to kind of have a way to predict whether a single pass is completed, okay? And that might be much easier to simulate, and then you can kind of build up an entire game based off of these smaller components type of thing. Okay, let's see. Let's keep going, and we'll. So the rest of our class is going to focus on kind of the rules behind calculating theoretic probabilities. Okay. But you could take an entire course on simulations, which is all about creating computer programs to kind of generate these empirical probabilities based on simulations. And you can also take courses entirely devoted to probability and learn much more complicated rules behind these theoretic probabilities. We're going to spend this week covering some of the basic rules of the theoretic probabilities. Okay, so we're going to have kind of rules for probability. And this is the theoretic All right, and so you know, we've kind of started off and we said, you know, probabilities. The probability of an event. So if I designate an event A is written, and we can write this probability of A, or also just kind of P of A, all right? And we've already said that any event, probability of A, must be between 0 and 1, okay? So if, and then maybe kind of designate, if the probability of A equals 0, then A is impossible, or A never happens. If probability A equals 1, then A is certain, or A always happens. Okay, we have kind of what we consider the OR rules, or the OR rule, which is if we have two events, A and B, we say the probability that A or B happens is probability of A or B, okay? And we, the formula to calculate the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Okay. And there's a special case of this rule. Okay, and that is, we say events A and B are called mutually exclusive if the probability of A and B equals 0. Okay? So what does it mean that the probability of A and B equals 0? It's impossible. That means event A and event B happening together is not possible. Okay? So if A happens, then B cannot happen at the same time. So a simple example would be the coin lands heads is event A, the coin lands tails is event B. Okay? You can never flip a coin and have it land both heads and tails at the same time. So those outcomes are mutually exclusive. Okay? Or if we are talking about drawing a card from a deck, the outcome that the card is hearts and the outcome that the card is spades, those are mutually exclusive. You cannot have a card and have it be both hearts and spades together. So those outcomes are mutually exclusive. Okay, so events A and B are called mutually exclusive if this is the case. And so if A and B are mutually exclusive, then the probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B, but the probability of A and B is 0, so this becomes just the probability of A plus the probability of B. Okay, so it's the same rule, but because A and B is now 0, for mutually exclusive events, you can just add those two probabilities together. All right, is this okay? All right, so we'll just try a few examples. I'll give you guys a moment to catch up on your writing. So let's imagine a deck of cards. So we have a deck of cards, and we're going to just draw one card at random. Okay, so we're going to define a few outcomes. We'll say A is the card is hearts, or the card is a heart. B will be the card is black, and we'll say C, the card is an ace. Okay, so over here, well, I guess there's another rule that maybe seems obvious, but I didn't. Maybe I'll explicitly state it. We can say, the probability of some event with simple outcomes, okay, is equal to the number of simple outcomes included in the event divided by total number of simple outcomes. Okay. And simple outcomes are outcomes that are equally likely. So for example, in a deck of cards, all 52 cards are equally likely. They can all be considered simple outcomes. Okay, so using this, what is the probability of A? Probability of A is the probability that the card is a heart. How many hearts are in a deck of cards, and how many cards do we have total? Yeah, so it'd be 13 out of 52. 13 cards are hearts, 52 cards in the deck total, and this is 1/4 or 0.25. Okay. Probability of B would be the probability that a card is black. How many cards are black? 26 out of 52, so 1/2, and the probability there is now 0.5. And the probability that a card is an ace, four out of 52, or 1 out of 13, which 0.077. Okay. All right, so then what if I ask the question, what is the probability that a random card is a heart or is black? Okay, so this would be the probability of heart or black. Okay, so go ahead and take a minute to solve this problem. Okay, and what do we have? Correct. So we have probability that a card is heart or black. This would be the probability of heart plus the probability that the card is black minus any overlap, heart and black. Okay. The probability that the card is a heart is 0.25. The probability that the card is black is 0.5. Can a card both be a heart and black at the same time? No, these are mutually exclusive events, so the probability of heart and black is 0, and so we get 0.75. Yes, question?
Yes, I don't understand how you got the 13, 26, and 4 when we were finding out which one was heart, black, or ace.
Oh, okay. Maybe I assumed. Are you familiar with a standard deck of cards, or less? Not really. Oh, okay. All right. So that's my bad. So let me see if I can look at a deck of cards. Complete deck of cards. We'll go to. Maybe this counts. Okay. So there are 52 cards in a deck. Okay, and they're divided into two colors: black cards and red. Black cards and red cards, and it's also divided into 4 suits. Okay. There are clubs, diamonds, hearts, and spades, okay? And out of the 52 cards, 13 belong to each suit. So you have 13 clubs, 13 diamonds, 13 hearts, 13 spades, okay? And then we have, there are, 13 different ranks from ace through king, and there are 4 in each rank, okay? And so I suppose if you looked at this picture, which I just found by searching for a complete deck of cards. I don't mean to go to his webpage. If you look at this picture, this is how we've determined how we got 13 cards are hearts. Okay, how many cards are black? If we count these up, there's 26 of them. And how many cards are aces? There's 4 that are aces. Okay. Okay, so that's how we got these values here. Okay, so we have that. I'm copying over this part just for note's sake. Okay, I can ask another question. What is the probability that a random card is a heart or an ace. Okay? What is the probability that a random card is a heart or an ace? So I'll give you guys a moment to figure this out. And maybe if you need this diagram here. Oh, whoops. Card is a heart or an ace. Oops. Okay, and what do we get here? Or do you guys need another minute to figure it out? Huh?
133.
I think maybe you're forgetting to do something.
Oh, no, I yeah, I must have any number about that.
So I'm getting 0.308, 0.308, I think. Okay, or 16 out of 52. All right, let's break this down here. Okay, so this is going to be probability. Let me use a different color here. So this is going to be the probability that a card is heart or ace. Okay, which is going to equal probability of heart plus probability of ace minus the probability of, I'm just going to write heart and ace like that. Is that this is an and sign. Okay? So the probability that a card is a heart is what? This is going to be 13 out of 52. And the probability that a card is an ace is 4 out of 52. And then we have to subtract off the probability that a card is a heart and an ace. So we have to subtract off 1 out of 52. Okay? And so this gives us 16 out of 52, or 0.308. Okay? If we wanted to kind of manually check this ourselves, all right, we could go through and circle every card that is a heart or an ace. Okay, and so this is an ace, this is an ace, this is an ace, and this is an ace, and all of these ones are also hearts. Okay, so I'm just drawing circles around all the cards that are hearts or aces, and if we count them up, we see there's 1, 2, 3, 4. And I count all of these up, there's 12 more. We have a total of 16 cards out of 52 that are 16 out of 52 are hearts or aces. And we can see that if I were to simply just add 13 and 4, I would be double counting this ace of hearts. Okay? And so that's why I need to subtract off the overlap. Okay. Are we feeling okay with this? All right. Yes, question?
When we do and,
Mm-hmm.
we just have probabilities of hearts and aces, and we didn't use a fraction, how would we, because it's obviously you're not subtracting the two probabilities. So you're not...
Correct. So calculating and probabilities is a little more challenging. You either need to have the the breakdown for you, or other things, and that's actually the next slide that I'm going to do. Okay, But that's a good question, because if we didn't have this picture of the deck of cards and we didn't know that there was one card that was a heart and an ace, like if a deck had two aces of hearts or something like that, then we would be in trouble. Yeah. Okay, so let's continue on here. We'll talk about and probabilities. Okay, so and probabilities, that we would say the probability of A and B is equal to the probability of A times the probability of B given A. This symbol, this is read as, read as probability of B given A. Oops. Okay, and what probability of B given A means is this is the probability that B will happen if we know, or if it is given, that A has happened, or or will happen. I'll just leave it as has happened. Okay, so it's the probability that B will happen if we know that A has happened, and that is the probability of B given A. Okay, and so so this is what we have. And then there's also a special case, and this is if A and B are independent, which is very different from mutually exclusive, okay? Okay. If A and B are independent, that means the outcome of B has no influence on the outcome of A and vice versa, or the outcome of A has no influence on the outcome of B. I'll just write the outcome of one event has no influence on the outcome of the other event. Okay, so what does that mean when it comes to the math? What that means is that the probability of B given A, okay, the probability that B will happen if we know A has happened is just the probability of B, meaning that the outcome of A, whether A has happened or not, doesn't influence us, okay? B doesn't care. The probability that B is going to happen is the probability that B is going to happen. It doesn't care if A has happened or not. So the probability that B given A, that's just the probability of B. I could say the probability of B given not A, okay, that A hasn't happened, this is also going to be what? The probability of B, okay? And so when we apply that to our AND probability rule, so if A and B are independent, then what happens? The probability of A and B will equal the probability of A times probability of B given A, but the probability of B given A is just the probability of B. Is that okay? Yes, question.
That bottom statement is different from the top one, right? 'Cause it's a special case.
Yeah, the top case, this is always true, but then we have a special case where sometimes the probability of B given A is just the probability of B, and that's when A and B are independent. And if that's the case, this top thing boils down to this thing. Okay? All right, so let's try this out. There was one rule that I forgot, okay, and this is the complement. Complement is the event that A does not happen. Okay, so we can write this as not A, or it can be written as A complement, or sometimes A prime. Okay, and the probability of not A is equal to 1 minus the probability of A. Okay? Notice these up here, these are events. Okay? Do not assign numbers to events. Okay? If A is the card is hearts, then A is the card is hearts. Okay? Only assign numbers to the probability of that event. So it's not correct to say A is equal to 0.25. You'd say A is the probability. A is the event that the card drawn is a heart. The probability of A is equal to 0.25. So there is a distinction. So these are events, and these are probabilities. Okay, so let's combine our understanding of the multiplication rule for the AND events along with our given probabilities and kind of come up with a situation here, okay? So, let's imagine you are going to travel, okay? So travel at the airport. Okay, and let's say if there is a storm, the probability of a delay is, with a storm, let's say the probability of a delay, I don't know, 60%. Okay, this is going to be a bad storm, all right? And on the other hand, if there is no storm, the probability of a delay is only 10%, okay? And we will say, the forecast says there is a 35% chance of a storm. Okay, so I'm going to ask, what is the probability that your flight gets delayed? Okay. So I'm going to answer this question using a tool called a probability tree. Okay, so this is a, all right. But let's kind of list off the, let's identify these values. If there is a storm, the probability of a delay is 0.6. What is this? How can we label this symbolically? This quantity would be the probability of a delay given vertical bar storm, okay? So this is the probability that there is a delay, the probability that a delay happens given or if it is known or if a storm has happened or happens, okay? Is that okay? All right, so what would I write for this one? 10%. This is the probability of what? Probability of delay given no storm, okay? And what is this? 35% chance this would be this is probability of a storm. Okay, so I'm going to draw out this tree here. And we're going to say there are two things that could happen. Either there's a storm or there's no storm. Okay, so the probability that I go down the storm path is 0.35. Okay, what is the probability then that there is no storm? 0.65, right? You know, 1 minus 0.35 is 0.65. So it's, there's either going to be a storm or there's not. These are the only two outcomes. So, you know, a handy thing is that the nodes, the probabilities coming from any node must add up to 1. Okay? All right, if there is a storm, then there could be a delay, or there could be no delay. All right, and if there's no storm, it's still possible that my flight gets delayed, but there's also the possibility that it doesn't get delayed. Okay, so these are the outcomes that could happen. All right, so if there is a storm, what's the probability we go down the delay path? 0.6. Okay, so what's this probability that goes over here? 0.4. Okay, if there's no storm, what's the probability I go down to the delay path? 0.1, which means the probability that I go down this path would be 0.9. Okay. All right, so then 0.35 I'm going to label. This is the probability of a storm. And over here, 0.6, this is probability of delay given storm. Okay. This 0.4, this would be probability of no delay given storm. Okay. And you can go and you can fill out all of the labels, but I just want to kind of illustrate this. Okay. So I can say the probability of a storm and delay is equal, okay? So if we just flip back in our notes to, you know, what's the probability of A and B? It's the probability of A times the probability of B given A, right? So this would be the probability of storm times the probability of delay given storm. And so this would be 0.35 times 0.6. So I just do that, and the answer I get is 0.21. Okay, so I can actually, with the way the tree is set up, I can just go down the paths, and effectively I'm doing the math in these formulas. Okay, I can just do 0.35 times 0.6, and that gives me 0.21. 0.35 times 0.4, I would get 0.14. Okay, 0.65 times 0.1, I get 0.065. And over here, what would I get? I would get 0.585. All right. Yeah, okay. Okay. So, well, I suppose I'll still label these. So this would be the probability of, what would the label here be? Of 0.14 is equal to the probability of storm and no delay. And I want you to be very clear in knowing that storm and no delay is very different from no delay given storm, which is also different from storm given no delay. Okay, these are all very different interpretations. It is, you can, inside an and thing, you can switch them around. Probability of a storm and no delay is the same thing as probability of a delay and no storm. Okay? But it's very different from having an and sign and a vertical bar for given. And when you have the given notation, it's very different if you switch the two events in front and behind the given bar. Yes?
Would it be no delay and storm?
Oh, I'm so sorry. No delay and storm. That was my bad. Thank you. Good catch. Okay. And so 0.65, this would be probability of no storm and delay. And this is probability of no storm and no delay. Okay, but we still haven't answered our original question, which is, what is the probability that your flight is delayed? Okay, so there are, what's that? Yeah, so there are two ways I could get delayed, okay? There could be a storm and I get delayed, and that's this number. There could also be no storm, and yet, the airline doesn't have their stuff together or whatever happens, and I could still be delayed even though there's no storm, right? So the probability of delay, the overall answer for probability of delay, is going to equal the probability of storm and delay plus the probability of no storm and delay. Okay. Now, do I have to worry about any overlap? Because whenever we do kind of these, A or B situations, we also have to subtract off any overlap. Is there any overlap between these two things? No, you cannot have experienced a storm and a delay and at the same time have experienced a non-storm and a delay. So there's no overlap for us to worry about. Okay, so these are mutually exclusive outcomes. And so our answer is 0.21 plus 0.065, and I get 0.275. This is the overall probability that there is a delay based on our initial set of conditions. Is that okay? All right. I'm going to copy this chart onto the next slide, and I'm going to ask another question here. Okay. So using kind of the same, using the same information. Okay. Now pretend you are at the other airport, picking your friend up. Okay. And so we say your friend's flight is delayed. Okay, what is the probability that there is a storm? Okay, so this is a different question, right? So now we're waiting, and we say, oh, okay, status delayed. We can then go back and say, well, what was the probability that there was a storm? So the thing that we're going here now is, what is the probability of a storm given that there was a delay? Is this okay in terms of interpreting this question here? What is the probability that there was a storm, given the fact that our flight was delayed? Okay. All right, how can we answer this? Okay, so what would we do? Okay, well, so let's step back for a second. Okay, so we had. So I'm gonna flip to a new slide here. Okay. So earlier we said the probability of A and B is equal to the probability of A times the probability of B given A. Right? So this was our rule from earlier. Okay? Well, we can do some quick algebra, and in this situation it was assumed that we were given A and we are given B given A. But we might have a situation where this is the piece of information that we want, and we have the other bits of information. Okay? So we can flip things around, and this is known as Bayes' rule. And we can say the probability of B given A is equal to the probability of A and B divided by the probability of A. Okay, so all I've done is just divide both sides by the probability of A. And so now I can get this thing by finding this. Okay? And the labels of A and B are completely arbitrary. So before, we might have said A was storm and B is delay, but we could flip these around and say B is the storm and A is the delay. Is that all right? Okay. So just rearranging a few terms, we can use this to go back and answer a question. All right? Okay, so we've got probability of storm given delay. So using that rearrangement of terms, we can say this is going to be equal to, on the top, I'm going to have storm and delay. And what am I going to divide by on the bottom?
Delay.
By delay, okay? So, just on the other thing I said, it was probability of B given A is equal to the probability, here I'm going to choose a different color just to kind of illustrate this. So I had probability, I think I said B given A is equal to the probability of A and B divided by the probability of A, right? Okay, so all we're going to do is we're just going to say B is storm, A is delay. Okay, and so we're just filling in where we see storm and delay, and so we see, okay, delay goes on the bottom here. So is this okay, going from here to here? All right, so then what is the probability of getting a storm and a delay? 0.21, right? Probability of a storm and delay is what happens if I go down the path, and this path. On the numerator, I'm going to have 0.21. Is that okay? And then on the bottom, what do I have? What's the probability of a delay? So we found this on the previous problem, right? So this from the previous problem. We found this was equal to 0.21 plus 0.065, okay, which was 0.275. So on the bottom, the probability of a delay is 0.275. Are we okay with this progression here? All right, and so our final answer is going to be 0.21 divided by 0.275, 0.763. Yes?
I mean, the probability of the storm / delay, it's the same order as the previous question, but the difference was it's just asking us the probability of the storm. Like, what's the difference? Like,
Okay.
like, how do you know when to divide it instead of multiplying it, I guess? I'm a little confused.
Okay, so wait, so we had, so notice these are probability of delay given storm, so, and that's 0.6. And over here we have storm given delay, and that's a different thing.
Okay.
Is that, so I'm sorry.
There's a delay because of the storm, and this is...
So over here is, if it's known that there's a storm, the probability that we end up getting delayed is 0.6. Okay? Over here, this is if it's known that the flight is delayed. So you know, just imagine you're at the airport and you look at the sign and it says the flight's been delayed. Okay? The question now is, what was the probability that there was a storm? Okay? So we're kind of trying to reverse engineer, you know, was there a storm or not? So that's a different question, okay? But yeah, you know, they do look very similar, and this is probably a very common mistake that students make, is that you know, getting storm given delay mixed up with delay given storm, and they do look very similar, but they are very different. The questions that they represent are very different, okay? And so so I think maybe I'll give you guys an exercise for you to try to work through and kind of just make sure you understand all of this stuff, okay? All right, so we will okay, I'm just gonna make this up. So we will say if a woman is actually pregnant, okay, a pregnancy test will report, and just so we can distinguish between the concept of pregnant and what the pregnancy test reporting pregnant, we'll say the pregnancy will report plus, okay? So if a woman is actually pregnant, a pregnancy test will report plus, and we will say these are not high quality tests, okay? So this will say with probability 0.98, okay? So, you know, most modern pregnancy tests are like 99 point something % accurate and have false rates of, you know, very low, okay? And again, this is a bad test. So, and if a woman is not pregnant, okay, the pregnancy test will report minus with probability 0.99. Okay. And we'll say the test only reports plus or minus, okay? And then I don't know how the woman knows this, but we'll say a woman suspects there is a 20% chance that she is actually pregnant. Okay, but I don't know how how anybody could come up with such a number, but you know, just for the sake of this illustration, we'll say that that's what she figures. Okay, so there will be there's two questions that I want you to try to answer. We'll say what is the probability that a test will report plus, okay? And then if a test does report plus, what is the probability that she is actually pregnant? Okay. So you know, this is kind of a silly example, and these numbers, you know, 98%, 99% sound pretty good, but if there were to be a test on the market with these numbers, they would be extremely bad tests and probably liable to some kind of class action lawsuit or something. So the accuracy rates are much better than 98, 99% these days. Okay, so go ahead and try this out. I'll give you guys a few minutes. If you're watching this on YouTube or whatever, I'm going to pause the video here just so there's not a whole bunch of blank space. So, so I recommend you pause the video on YouTube as well, because when I resume, we're going to go over the answer. All right, so but we'll go over the answer now. All right, and so the way we should set up our diagram is she is, you know, actually pregnant. Okay, or not pregnant. And we will say she is actually pregnant with probability 0.2, and she is not pregnant with probability 0.8. And then the test can either report positive or minus, okay? So the test reports plus or minus, okay? And I went with that rather than saying pregnant or not pregnant, because I think it would just be confusing to have pregnant, not pregnant, pregnant. So these are the test results, okay? And so if she's actually pregnant, it will report plus with probability 0.98, and will report minus with probability 0.02 then, okay? And if she is not pregnant, it will report minus with probability 0.99, but it will still report plus with probability 0.01, okay? So we can go down and we can multiply these things. Really, just to answer this question, what's the probability that a test will report plus? We only have to multiply the ones related to the plus, okay? So that's going to be 0.2 times 0.98, and over here, 0.8 times 0.01. Okay, so 0.2 times 0.98 gives me 0.196, and over here, I get 0.008. Okay, and so I would add these two together and say the probability of getting plus is going to be 0.196 plus 0.008, which is 0.204. Okay. And then, so what is the probability that she's actually pregnant? Okay, that is going to be the probability of pregnant given plus, which in our case will be the probability of pregnant and plus divided by the probability of plus, okay? So pregnant and plus is 0.196. That's this one up here. The probability of getting plus overall we found in the previous part of the problem, 0.204, and so our answer is 0.196 divided by 0.204, and we get something around 96%. Okay, let's just round it off to 3 decimals, and if you kept more decimals, that's fine, or if you didn't, that's also fine. So, okay, I hope that was helpful in kind of solidifying these concepts. Let's take a 10-minute break here. We'll come back at 8:45, and we'll finish out chapter 3.